Welcome back to the course on architectural design of ICs. So, in the last class we have seen this, that means in one particular circuit how we can implement this 1's complement as well as 2's complement. So, now we will see that means some of the architectural, that means changes to that means to handle the problems, how we can change the, or how, that means what are the tips or what are the tricks we can do so that we can avoid some of the, that means critical condition whenever we are designing the circuit. Okay. So, this is something that means apart from this architecture to that means algorithm to architecture mapping, but this is very much necessary whenever you are working to meet the specification. Okay. So, suppose you here consider one case, okay, where this is one algorithmic, this one is one algorithmic description which is given to you. So, that means this algorithm says that case state is when wet state, then the condition is that if this critical, then target will be selected from source 1, otherwise if it is not critical, then target will be selected as source 2. So, that means in one particular, that means there are two state when there is wet state and active state. In wet state, if the condition is critical, at that time the source 1 will be selected to the target, otherwise source 2 will be that means selected at the target. If when that is in active state, at that time this critical will be set to source 1, otherwise target will be set to source 3. Okay. So, that means here if you see that in any of the case, in any of the state, whenever I find that critical, at that time this target is basically selecting to source 1. Okay. Otherwise, it is basically selecting this source 2 or source 3. In active state or in wet state, so now this will be the corresponding circuit implementation for this particular logic. Okay. So, that means in critical condition, either it has to select this source 1 or select source 2 for this wet state, or in critical case in active state what will be the case, this source 1 and this will be source 3 for the condition of the critical. So, as I can see that this from this particular expression, critical is the case where in both the state it is common and it is selecting to source 1. So, I can write or I can modify the same, that means algorithmic description in this manner, that is if critical, then target equals to target you set to source 1, otherwise you just wait for the state to be checked, that is in wet state choose target source 2 or in active state you choose target equals to source 3. That means at that time the critical will select between the state or source 1. Then what is, that means what is the problem here? In a critical case, I need immediate action to be done. Okay. So, here in this algorithm description, what is the problem? It has to check the in which state it is first, and then it will check whether the condition is critical or not. So, that means in critical case I have to wait for some time to check whether that is the state, whether that state is in wet state or in active state. But instead of that, I can do the modification in such a way, so that whenever I am getting critical case, automatically this source 1 will be set to as both the things in both the state the target is selected to source 1 only, that is why I can only select this critical equals to target which is mentioned as source 1, and in other case you just chose, that means whenever this condition is not critical, at that time you wait and find out in which state it is, and then you select the corresponding target as source 2 or source 3. Okay. So, this method is known as prioritization. Okay. So, then another example of this late arrival signal, that means suppose one signal is coming or appearing to the corresponding critical circuit lately. So, how we can handle those situations? Okay. So, then consider another example of that. So, in another example of that, here if you see this another algorithmic, that means description, it is given to you. Begin if a underscore late plus b greater than equals to max, then out equals to c, else out equals to d. That means a underscore late means a is the signal which is coming lately or which is arriving to this particular logic lately. It has to be added with b, the value will be then checked with max. If the max value is, that means if this condition is satisfied, then out will be selected as C, otherwise out will be selected as D. So, what will be the circuit implementation? If I just implement this particular logic using the circuit or using the architecture, if I just draw for this particular logic. So, at that time what I need? A underscore late plus B first. So, A underscore late plus B first, then that has to be checked with max. So, that has to be checked with max. So, those is basically one single input, that means one bit input, sorry, one bit output, depending on this particular condition. If it is true, so if it is true, then it will select C, otherwise if it is false, then it will select D. So, there is a mux which is basically the select signal is this one. So, then what is the problem in this particular circuit? Suppose for this particular case, if I just draw the circuit again, that means A underscore late and this is B, then that has to be checked with max, and there is a mux depending on C and D, this will be selected. Now, consider one case where A late signal is basically coming lately. So, that suppose this is coming after 5 nanoseconds of delay. Okay. So, this is the addition operation. So, as this signal itself it is coming 5 nanosecond delay, and let us consider this as 5 nanosecond delay. So, that means after 10 nanosecond I will get the signals over here, and then it will be compared with max in this particular case. Let us consider this comparison takes 2 nanosecond. So, after 12 nanosecond this select signal is available to this particular mux. So, based on that, now suppose this has 1 nanosecond of delay. So, after 30 nanosecond I will get the corresponding output at this particular time. Okay. So, instead of doing that, can I save or can I reduce this particular 13 nanosecond which is requiring here? Can I reduce it? Or if I can reduce it, then how can I reduce it? So, if you just go back, so if I just change the logical expression in other way, that means this equation now if I just, that means change it, B minus, sorry, this B minus max, here what is that? A underscore late plus B, that has to be checked with max. Now, what I am doing? Max I just put on the left hand side and A underscore late I just put on the right hand side. Okay. So, now what will the equation will be something like this: B minus max, that is greater than equals to A underscore late, then out equals to C, otherwise out equals to D. That means the logic remains same. Here if you see, the logic remains same, but I just the position of A underscore late and max I have just changed, interchanged. So, now what is happening? For that, what I need? B minus max first, then that has to be checked with this with this A underscore late, and that particular select signal will choose C or D. Okay. Now, if I just again go back to the, that means slide here. So, now what is happening? So, here if I have just changed the logic. Now, according to the newer logic, what will happen? So, I have to consider max and B, max minus B, and then that has to be checked with A underscore late, that will become to this marks. This is C and D. So, this is basically appearing after some time. Okay. So, this has 2 nanosecond. So, whenever this signal is basically arriving at this 5 nanosecond, by that time I have already completed this 5 nanosecond work. That means, whenever this A late signal is arriving at this particular point, this 5 nanosecond, that means this job is also done at that particular time. So, here also I am getting at that particular, that means at that time this is done at within this 5 nanosecond. Now, this is 2 nanosecond, and for this marks what I need? I need another 1 nanosecond. So, here total to the, that means input to the output, how much time I require? 5 plus 2 plus 1, that is equals to 8 nanosecond. So, initially what I need? I need 13 nanosecond, but here I need 5 nanosecond. That means, the change what I did is that keeping the, that means the logic, keeping the logic same, only the expression I change from, that means I interchanged, and what happened? Instead of adder here, I put the, that means subtractor here. Adder subtractor has both the same delay, rest of the things remain same. Okay. So, that means now I can achieve or I can improve the corresponding frequency of my circuit. Okay. So, that means this is one technique. Whenever I am doing this algorithm to architecture mapping, the algorithm was defined in such a way, so that it is taking direct implementation of it, it is taking too much of time, but manually if I change something like this, so at that time I can reduce the time, that means reduce the things. So, here what I did the prioritization, that means because of this signal is coming lately. So, that is why I just before arrival of this particular signal, the job initially I have done, I am just completing the job beforehand of this particular signal arrived in this particular circuit or in this particular operation, and then I am doing the rest of the operation. Okay. So, this is one simple example by which I can easily get the benefit of improvement in the speed. Okay. Then again, if I consider another example. Okay. So, this that means this is the previous case was for how you can improve or how you can save the time. Okay. So, here we will see another example where I can save the area by using this resource sharing operation. Okay. So, this resource sharing operation, suppose one algorithm I am having something like this: process x y z select. If select signal is 0, at that time the output will be x star y, that means x multiplied with y, else y will be multiplied with z, that will be gone to the output. So, the direct that means implementation of this particular that means code is something like this: x star y, y star z, that means x multiplied with y and y multiplied with z is done here. And then I need one mux whose select signal is this SCL. So, if it is 0, then it will select x multiplied with y at the output, otherwise it will select y multiplied with z at the output. So, instead of doing that, okay, what I can do, that means from this particular code, if you follow in this multiplication x star y and y star z, both this y is common. So, at that time can I do something, okay, so that I can reduce the area more? How can I reduce? The first approach is that because multiplier needs more area, okay. So, in compare with multiplexers. So, what I am doing, instead of putting the select signal at the that means operator level, if this corresponding inputs, whether that is x, y or y, z, if I put the select signal, that means if I put the mux here, that means if I put the resource sharing on means in one multiplier, how can I that means implement both the function. So, how can I implement? So, here I am requiring only one multiplier, then what I am doing? So, what I am doing basically, so I have the logic select equals to 0, at that time r equals to x star y, otherwise r equals to y star z. Okay. That means otherwise means if select equals to 1. So, the direct implementation we have seen. So, the indirect implementation, if I just want to use only one multiplier, because there I need two multiplier, if I want to use only one multiplier. So, at that time what I can do? I am having only one multiplier, right. So, and it has to be 2 input. So, at the very first what I need? I need one mux, and here also I need one mux, correct. So, this is select and this is also select. So, at the very beginning what is there? That it needs x will be multiplied with y. That means, here if this is x and if this is y, then x is multiplied with y. And if select equals to 1, that means at that time what I need select at this when select equals to at that time what I need y multiplied with z. Okay. So, that means here select value equals to, when select value equals to 0, at that time I need, this is for 0 and this is for 0, and for select equals to 1 this is for 1 and this is for 1. So, whenever this select value equals to 0, at that time this will select x, this will select y. So, I will get x star y. When this value is equals to 1, so at that time this will cross, this will select y and this will be selected z. So, at that time I will get y star z. So, that means now initially in the initial implementation, what was the, that means cost of area? I need 2 multiplier plus 1 marks, right. In this particular implementation, what is the cost? Cost of area, that is 2 multiplexer plus 1 multiplier. So, can I reduce it more? Yes, I can. How? If you see, y is basically common in both the case. Okay. So, that means now I will select whether I need x will be multiplied with y or z will be multiplied with y. So, if I just take this as this is the multiplier. So, I need 1, y is basically fixed here. So, here I am having x and z. So, select, this is when select is 0. So, at that time it will select y. So, if select equals to 1, so y will be multiplied with z. So, that means x star y when select equals to 0, when select equals to 1, at the time y star z. So, here what is the cost? 1 multiplier plus 1 multiplexer. So, that means by this method, okay, now I can reduce the area. So, this is a simple trick. The code remains same or the functionality remains same, but using the tricks or using these tips or the techniques, I can reduce the cost of the area in this fashion. Okay. So, that means if one multiplier cost is let us say 10 unit. So, for the case 1 and for one multiplexer, if it is consuming 2 unit of area. So, for case 1 I need 22 unit area, for case 2 I need 12 unit area, sorry not 12, that was 14, 2 multiplexers and 1 multiplier, 14 unit area, and for case 3 I need 12 unit of area. So, that means now from 22 to 12, so 10 unit of area I am just saving by this method, resource sharing and operand alignment technique. Okay. So, this is just one simple things which we follow whenever we design the digital circuits. Okay. So, then here you see that with resource sharing, okay, with resource sharing what is happening? That means what is happening? Okay, this is another example. This is another example. Here you see that means x, y, z, okay, x, y, z, and this is select input, and whenever this here instead of in the previous case it was multiplied, here we have to check the equality. Okay. So, equality says that if x equals to y, then equal will be goes to 1, otherwise it will check z equals to t and those value will be gone to the output. Okay. So, the direct implementation says that x is basically first checking with y, that is scalar unit, that means 1, and z is basically that means compare with t, and then that has gone to the marks. If select equals to 0, then it will select this particular line. If select equals to 1, then this will select this particular line. Okay. So, that means here what I need? I need, if I consider, that means this bus. So, at that time what is happening? I am requiring one 16 bit. If this x, y, z and t all these are of 16 bit. So, at that time I need the comparison of this, and then that will be produce this 1, and then this is gone to the marks. So, that means here without, that means this is without resource sharing, correct. Now, if I just want to share the resource, that means if I am having only, if I use only one comparator block. So, at that time what will happen? I have to choose at what time the operation will be different, right. So, here I am having only one of this particular comparator block. Okay. So, the same thing if I just draw the circuit. So, at that time what is happening? I am having only one comparison block, right. So, now I have to select which input I have to compare. Okay. So, at the very beginning what I need? It has to be it has to be compared with x and y, and in the next it has to compare with z and t, right. So, that means what I need is that I need to compare with, I have to select this okay, and then I have to compare and this. So, sorry, not this one, this x and y here, this will be z, this will be t. So, this is 0, this is 1, sorry, this is 0, this is 1, this is 1. Okay. So, whenever this select equals to 0, at the time from here it will select x, from here it will be select a y. So, it will be selected and it will compare x equals to whether that is equals to y. So, here if I consider this x, y, z and t, each of this of 16 bit. So, at that time this is of 16 bit and this is of 16 bit, okay, and this is 16 bit 2. So, that means now initially what was there? Initially I was having two comparator, which is basically comparing here x and y, here y and z. This was the direct implementation and this one was the marks. So, and this is the select line. So, each of these was 1 bit, this is also 1 bit because this is comparison results. So, comparator results. So, this will be 1 only, and then this marks equals to this is 1 bit mux I need. Okay. So, if I consider, that means 1 bit mux cost, let us consider 1 unit, and 16 bit comparator cost is, let us say, 10 unit. So, for this particular case, for case 1, where I have not used resource sharing operation. So, at that time, what is the, that means corresponding area? Here I need 2 of this. So, 20 plus here what I require, that is 1. So, that means total 21 unit. In this particular case, with when I have put the resource sharing option on. So, at the time for case 2, what will happen? Here I need what? 16 into 16 plus 16, that is 32 plus 16 here, that is 10. So, total 42 unit of time. So, that means we use resource sharing operation, or that means option, to reduce the area, but here what is happening? Here I am getting, that means I am increasing the area, not only the area, here also I am increasing the delay. How the delay? Because for 16 bit multiplexer, the delay will be more, right. Here what is there? That is to this, that means any of this, that will come to the in the critical path, right. So, as this is 1 bit operation, so the delay for this and for to delay of this 16 bit operation, that will be more. So, that means as I am using more, is by putting the resource sharing option on, as I am consuming more area. So, that means I am that means losing the area as well as I am consuming more power. So, it is not at all true that all the time if I put this resource sharing option on, it will give you, or it will that means gives me the benefit of area saving. That is not at all true. It is the designer perspective that, or this designer intuition, that where he will use this resource sharing option on, whether that is beneficial for them or not, that here has to be checked, and what logic basically they are implementing, based on that we have to put this resource sharing option on or off. So, these are the tricks or tips which we use whenever we design any digital circuits. Okay. So, next classes, in the following classes, we will again see several kind of architectures or this kind of tricks and tips which are very much beneficial for digital design circuit. Okay. Thank you.